a couple of things that I showed one of your colleagues there. So the first thing was regarding the mixture. So this is the soccer distribution applet that I wasn't able to show you earlier. So in Safari apparently can be configured to work with Java. It does require Java. If I go down to the M for mixture, mixture distribution. So this allows me to go ahead and specify how many. Remember when I had x1 plus x2 plus x3 when I mixed them? That's what we're going to be doing here, but in a graphical way. So I can simply specify, suppose we want to have 3 of these guys, and it kind of gives you 3 different Gaussians put together. So I can specify their mixture parameters. So the first row has the mean. So the mean of the first one is -4, the mean of the second one is 0, and the mean of the last one is 4. I want to bring them a little bit closer together by, suppose, making this -2. -2. This one can stay at 0, and I can make this one perhaps 1. And then standard deviation, why do we make this one to be 2, 1, and then 3 perhaps. And now let's go ahead and load the last one. I want to give it a little bit of a higher weight. And now you see the weights always need to add up to 1. Right now they don't, but as I OK it, it's going to compute their sum and divide each of them by the total sum. So they're going to be adding up to 1. So you don't have to be exact here, but suppose I want this to be half. Suppose I want this to be half the impact. I can call it 0.4. And suppose I want the first one to be, well, 0.3, why not? Okay. And now you see, here is the mixture of the 3 distributions. Looking at this, if this was your histogram, you've got no idea that 3 things are co-generating it, do you? Right? Okay. Is that right here? And now this is because I overplayed it a little bit, right? Had I chosen more reasonable parameters, like for example, lowering this dispersion here to 1, and lowering this perhaps to 2. Now, okay, and this is even still too big, so maybe I'll give you I'll leave a hint of the 3 distributions. Something like this, okay? So this is your process. And you're hypothesizing there is probably 2 populations. Now we know there is 3 populations in here. Crystal clearly defined, right? So that's what a mixture model is. And with the mixture model, you can do the same inference as you did before. So for example, grab the mouse, click somewhere, and I know that below this value, I have 27% of my data. And then I can do this above as well. Above 3.34, I have 6% of my data, and everything in between. So you can do exactly the same inference as you can with a normal distribution, right? P-values, well, tail probabilities, you know, the same deal. Now, what I also wanted to demonstrate is that if you go to the modeler, okay, that's what the modeler looks like. And I'm going to go ahead and go again to the mixture distribution. Go back to my 3 cases. Okay, go back to my 3 cases. Okay, so what did we have? We had, I believe, -2, 0, and let's make it 2. Let's leave them equal for now. And suppose I take 1,000 of these. Okay, so from my mixture that I just defined, I'm going to take a sample of 1,000 of these observations. They're going to be showing up right up here. Okay, can everybody see I've got exactly 1,000 of these? I should. $1,000 of these guys, positive, negative, mixed. Then if I go to graphs, that's the navigation is going to be a little difficult here. Okay, and I'm going to be scaling up and estimating the parameters. And now look what happens here now, you guys. It's very important. So, I know that I sampled from a mixture of 3 Gaussians, okay? But I'm fitting right now a beta distribution model. Let's go and change that beta to normal, and you'll see in a second why. And click estimate the parameters. And now this is going to tell me that if you want to fit a single normal distribution to this mixture of 3, the best parameters are mean of 0.14 and a variance of 3.7, which corresponds to a standard deviation of about 2. And then it says the Kolmogorov-Smirnov test, you know, they're not too distinct, right? The p-value is 0.99. I can't discriminate between the mixture of 3 normals and the single normal with these means and this standard deviation, okay? So here's the hypothesis that you test. So in other words, we have something here pretty good, but I want to go a little bit better, right? Suppose I want to go with a mixed, because in this case I know what the underlying distribution is, right? I do know because we're simulating here. So, and I'm going to say, you know, a mixture of 2, well, these are the 2, the green one and the darker green, and then the mixture is in red. Now, I know I have 3 of them, so let's go ahead and make that a 3 here. 10 iterations is fine. And now you see, this is a confused model, right? Model 1, Model 2, Model 3. Overall, it works okay, I suppose, looking at the results. But we obviously don't, oh my gosh, okay. Well, it fits in 2 very good. Oh, this is a 3 now. Here is one, the yellow one, the green one, and then the pink one. So it's almost right, except that this guy is too far out, right? This guy is supposed to be right up here somewhere. Is everybody here with me? So the stochastic, what we're doing here is we're doing expectation maximization model fitting of parameter estimations. Because we know that we have 6 parameters to fit, 2 for each of the 3 mixtures, mean and standard deviation. 6 parameters need to be estimated iteratively, and you see when you click reinitialize, each time it's going to give you different results. So in this case, it gives me that the first model has mean of -2.3. This is close to the -2 that we started off with. Its variance is 0.5. Kind of underestimating. The second model has a mean of 1 and a standard deviation of about square root of 2. Not too bad. And the third model, which was way off to the right, which was kind of off, has a very low weight, right? You see how low its weight is? But the mean is huge, 4.6, and the variance is small. So you can kind of play this game until you, okay, so that may be an okay model. Yeah, the mean is still too large, the weight is too small, it kind of wants to fit degenerate models, right? The weight of the first one is high, the weight of the second one is high, but the third component is very degenerate, right? It's kind of there, it doesn't help at all. So, you know, that's another 3. Now that may be the right one, if you know what I mean. So let's look at that. The purple, the green, and that darker green, they may be the right ones. Let's just have a look. Minus 2.5, slightly lower. Variance of 0.4 translates into a standard deviation of about 0.2. That's kind of low. The second one has a mean of close to 0 and a standard deviation of 1. So that's about right. That hit it right on. And the third one has a mean of 2.7 when in fact it was 2, I believe. And the variance is kind of small. So not too good, but kind of getting there, right? So does everybody see how we can kind of fit in? Yeah.
How do you figure out that it's not a better than
Oh no.
key values?
By visually, because remember we knew that the center should be at -2, 0, and 2. So I visually, but also remember also underneath here when you have the well, this p-value is actually significant that the model and the histogram are distinct. So it's not the model is not right, but visually at least it does look appealing. It's a bit too wavy. It separates them too much, but maybe that's what it is. Maybe they need to be untangled. I mean, remember the data, the 1,000 observations that I use as my data, this is just a sample of the real population that does look like what we are modeling here. So, you know, it's one of those things where when the sample does not agree with the model, doesn't necessarily mean the model is bad. And because in this case we have the benefit of the doubt of knowing what the underpinning was, this is probably reasonable to estimate.